Hello researchers, thank you for your hard work analyzing research papers today. Today we will delve into the application of propensity score analysis, an important methodology for the statistical analysis of medical papers. नमस्कार शोधकर्ताओं, आज शोध पत्रों का विश्लेषण करने में आपके परिश्रम के लिए धन्यवाद। आज हम प्रोपेंसिटी स्कोर विश्लेषण के अनुप्रयोग पर गहराई से चर्चा करेंगे, जो चिकित्सा पत्रों के सांख्यिकीय विश्लेषण के लिए एक महत्वपूर्ण पद्धति है। Welcome to this explainer. As medical school professors and graduate researchers, you already know that the absolute gold standard for clinical studies is the randomized controlled trial. But let's be realistic, we can't always conduct an RCT. Whether it's due to ethical constraints, astronomical costs, or simply the need to look at real-world long-term outcomes, we often find ourselves relying heavily on observational data. And that is exactly where propensity score analysis becomes absolutely vital. Today we're going to break down the mechanics, the assumptions, and the real-world applications of this method, ensuring you're equipped to handle treatment selection bias like a seasoned statistician.
We have a rigorously structured masterclass ahead of us today. We'll start with the foundations of propensity scores, move into Estimands and model building, and then tackle propensity score matching. From there, we'll explore inverse probability weighting, compare PSM and IPW, and finally wrap up with best practices and reporting.
Section 1. Foundations of propensity scores. Let's look at the core problem and the theory behind our solutions.
Right, let's get straight to the heart of the matter. In observational studies, patients aren't randomly assigned to treatments. A clinician makes a choice based on patient characteristics, which introduces an inherent treatment selection bias. To put it simply, the treated group and the control group usually look very different right out of the gate. So, how do we fix this? Enter the propensity score. We define this as the conditional probability of an individual receiving a specific treatment based purely on a given set of observed baseline covariates. By summarizing all these multiple observed baseline characteristics into one single, neat score, we can effectively group patients with similar scores together. In doing so, we are mimicking the randomization of a clinical trial. But, and this is a massive but that you must keep in mind before you even begin, you have to ensure you have an adequate sample size and that you've measured your potential confounders with high quality. Propensity scores can only balance the covariates that we have actually measured. They fundamentally cannot account for unmeasured confounders. That is the Achilles heel of this entire methodology, and it's something you must always acknowledge.
Now this brings us to the mathematical foundation of what we're doing. Our first core assumption is known as conditional independence, or sometimes you'll hear it called strong ignorable treatment assignment. For our propensity score analysis to hold any mathematical validity, we have to assume that the treatment assignment is completely independent of the potential clinical outcomes once we have conditioned on our observed baseline confounding variables. In plain English, we have to theoretically argue that we've captured all the relevant confounding variables in our dataset. If there is a massive unrecorded variable influencing both the treatment choice and the outcome, our assumption of conditional independence completely falls apart.
Moving on to our second essential assumption, positivity. This is a very practical constraint. Positivity dictates that every single unit in your study must have a non-zero probability of receiving either the treatment or the control. Think about it. We require a sufficient area of common support. That's the overlapping region in your data where both treated and untreated patients actually share similar propensity scores. If you have a situation with absolutely no overlap between your cohorts, say patients with a certain severity score always get the surgery and those without it never do, you simply cannot make a meaningful statistical comparison. In real-world practice, if a patient's positivity is violated, meaning their propensity score is right at 0 or exactly 1, they fall completely outside this common support. You have to exclude these extreme subjects from your analyses entirely. And when you write up your paper, you must transparently report exactly how many patients were excluded based on this criteria.
Section 2. Estimands and model building. This is where we define the blueprint of our study.
Before you run a single model, you absolutely must determine your treatment estimand during the study design phase. What exactly are you trying to estimate? Are you trying to find the average treatment effect, or ATE? This represents the hypothetical effect if your entire study population was forced to receive the treatment versus if they all received the control. We typically use inverse probability weighting, or IPTW, to calculate the ATE. Or perhaps you're looking for the ATT, the average treatment effect on the treated population. This asks, what was the effect of the treatment specifically for the patients who actually ended up getting it? For this, propensity score matching is your go-to method. There's also the ATU, the average treatment effect on the untreated.
It is incredibly important to understand that marginal methods like IPTW and PSM calculate fundamentally different parameters than conditional, covariate adjusted regression models. You cannot just run an IPTW analysis, run a standard adjusted regression, and directly compare the resulting odds ratios. They are estimating entirely different things.
So, how do we actually calculate this score? In most cases, we use a logistic regression model where the treatment status is the dependent variable. But you cannot just throw every variable you have into the model. You must adhere to strict variable selection rules. Rule 1. Variables must be measured prior to the treatment, baseline only. Rule 2. They must be associated with the clinical outcome. Rule 3. You must include all known clinically relevant confounders. Now here is a trap many researchers fall into. You must completely exclude instrumental variables and surrogate variables. An instrumental variable is something that strongly predicts whether a patient gets the treatment but has absolutely no relationship with the outcome. If you include these, you are just artificially inflating the variance of your propensity score and actually increasing bias. Furthermore, avoid mechanical stepwise selection algorithms. Do not let a computer mindlessly pick your variables based on p-values. Base your variable selection on a thorough literature review and your own expert clinical knowledge. To improve the balance in your model, you might need to include higher-order terms or interaction terms. And if you're working with complex datasets, modern approaches increasingly utilize machine learning, like boosted models, to optimally capture nonlinear relationships.
Section 3. Propensity score matching. Let's talk about constructing comparable cohorts.
The primary goal of propensity score matching, or PSM, is quite intuitive. We want to pair up treated and untreated subjects who have highly similar propensity scores to create perfectly balanced comparison groups. How do we do the pairing? The most common algorithm is nearest neighbor matching, often called greedy matching. It's called greedy because it takes a treated subject, looks for the absolute closest available control, pairs them up, and moves to the next, without considering the overall picture. Alternatively, optimal matching minimizes the global propensity score distance across the entire matched sample all at once. We also have full matching, which stratifies the entire cohort into sets of varying sizes, and exact matching, which forces perfect alignment on specific categorical variables. But I'll let you in on the secret. For the vast majority of clinical applications, simple greedy matching performs just as well as optimal matching, provided your parameters are correctly configured.
Setting those parameters is where the real statistical artistry comes in. Every choice you make is a strict trade-off between bias and variance. Take your matching ratio. If you do one-to-one matching, you minimize bias, but you throw away a lot of data. If you do one-to-n matching, pairing one treated patient with 2 or 3 controls, you increase your sample size and reduce variance, but you risk introducing worse matches, which increases bias. Generally, a 1-to-2 ratio improves precision, but pushing it beyond 1-to-4 usually offers very little benefit. Then there is matching with or without replacement. Matching with replacement allows a highly suitable control patient be matched to multiple treated patients. This decreases bias when your common support is very narrow, but it inflates variance. Finally, the Caliper limit. This is absolutely essential. You must impose a caliper to restrict the maximum allowable distance between matched subjects to avoid poor matches. The rigorous standard established in the statistical literature is to set your caliper at exactly 0.2 times the standard deviation of the logit of the propensity score. Memorize that number.
Section 4. Let's shift gears and look at inverse probability weighting and how we create a pseudo-population.
If matching is all about finding pairs and ruthlessly discarding the rest of your data, inverse probability of treatment weighting, or IPTW, takes a different approach. IPTW keeps everyone in the dataset, but it fundamentally changes their relative mathematical importance. We do this by applying specific inverse mathematical weights to every single individual. For a subject who received the treatment, their weight is simply 1 divided by their propensity score. For an untreated subject, the weight is 1 divided by 1 minus their propensity score. What this brilliant mathematical trick does is synthesize a balanced pseudo-population. In this weighted pseudo-population, the baseline covariates are perfectly balanced between the treatment groups, effectively simulating a randomized trial while utilizing every single piece of data you collected.
However, using those standard formulas straight out of the box produces what we call unstabilized weights, and this can be incredibly dangerous. Imagine a patient who receives a treatment completely contrary to all their baseline clinical characteristics. Their propensity score for that treatment might be tiny, say 0.01. Their unstabilized weight would be 100. That one anomalous patient would heavily distort your entire analysis. Therefore, you must apply stabilized weights. This involves placing the marginal probability of treatment into the numerator of the weight formula, which shrinks extreme values. Even then, you should meticulously assess the weight distribution before running your outcome models. If you still have extreme weights, you need to apply weight truncation, typically capping them at the 1st and 99th percentiles. Finally, when you run your outcome model using weighted regression, you have to be careful. Because IPTW essentially creates mathematical copies of patients in the pseudo-population, it introduces within-subject correlation. If you use standard statistical software out of the box, your standard errors will be artificially tiny. You absolutely must estimate your standard errors using robust sandwich estimators or bootstrapping techniques.
Section 5. Comparing PSM and IPTW. Which method should you actually use?
Choosing between these methodologies dictates your entire analytical path. Let's look at the breakdown. Propensity score matching is highly intuitive. It's very easy to explain to a clinical audience, and it estimates the ATT. However, because you are actively discarding unmatched patients, it drastically reduces your sample size, which inevitably yields wider confidence intervals. IPTW, on the other hand, estimates the population-level ATE. Because it preserves your full sample size, it generally provides narrower confidence intervals and greater precision. But, as we just discussed, it requires highly careful management of extreme weights. I should also mention older techniques like propensity score stratification or simply adjusting for the propensity score as a single covariate in a regression model. We now know that these are mathematically inferior for removing confounding compared to matching or weighting, and they are generally no longer recommended as primary techniques. Furthermore, if you're dealing with advanced longitudinal data featuring time-varying treatments, IPTW is truly the superior choice. You can combine it with marginal structural models or MSMs to properly adjust for time-dependent confounding, something matching simply cannot handle.
Section 6. Best Practices and Reporting. Let's make sure your paper actually survives peer review by avoiding some incredibly common pitfalls.
A comprehensive review of high-impact medical literature reveals that researchers make frequent, highly problematic methodological errors all the time. The single most fatal mistake we see is ignoring the matched pair structure after conducting propensity score matching. Once you match patients, they are no longer independent. You cannot use independent sample tests like a standard student's t-test or a standard chi-square test on matched data. It's mathematically wrong. You absolutely must use appropriate paired techniques: conditional logistic regression, generalized estimating equations, stratified Cox regression, or Migne-Mars tests. Other incredibly common flaws include hiding the pre-match baseline imbalances. You have to show us how bad the data was before you fixed it. Researchers also frequently fail to explicitly state whether they matched with replacement, fail to report their exact caliper width, or fail to state exactly how much their sample size was reduced post-matching. And as I mentioned earlier, utilizing automated stepwise variable selection or improperly including outcome-independent surrogate variables in your model will get your paper rejected by any rigorous statistical reviewer.
Now let's talk about proving that your matching actually worked. When assessing covariate balance post-match, the critical metric is the standardized difference. A standardized difference of less than 0.1 in absolute value is the universally accepted threshold for adequate balance across your covariates. I want to be unequivocally clear here. You must completely stop using p-values to assess baseline balance after matching. Why? Because p-values are highly dependent on sample size. Because matching inevitably throws away data and reduces your sample size, a p-value will artificially become non-significant even if severe bias remains, simply because the n is smaller. It is a mathematical illusion. Rely exclusively on standardized differences and vigorously supplement them with visual diagnostic tools. Reviewers love to see love plots, density plots, and QQ plots to visually confirm the balance across your cohorts.
To successfully navigate the peer review process, your manuscript needs to read like a transparent, chronological recipe. Phase 1. Detail your exact list of variables, your clinical justification for choosing them, and report the pre-match balance. Phase 2. Show the propensity score distribution histogram to visually prove to the reviewers that you have adequate common support. Phase 3. Detail your exact matching or weighting algorithm, including all parameters and the specific software packages used. Phase 4. Report the post-match sample sizes and prove your balance with standardized differences less than 0.1. Finally, Phase 5. Report your specific outcome estimates alongside their 95% confidence intervals, ensuring you've used robust standard errors where necessary. I highly recommend adhering to standard reporting guidelines, like STROBE, but you really should combine them with propensity-specific checklists to guarantee a mathematically robust submission.
As we conclude this explainer, I want to leave you with one final critical thought. Always remember the fundamental limitation of propensity score methodology. It is not magic. It only balances the covariance that you had the foresight to measure and record. You must continuously ask yourself, how might unobserved variables, perhaps an unrecorded genetic marker, a nuanced clinical severity metric not captured in the EHR, or socioeconomic factors, still be driving your final results? You are absolutely required to acknowledge and thoroughly discuss the potential impact of unmeasured confounding in the discussion section of your manuscript. Thank you all for your dedication to mastering these rigorous statistical methodologies. Your commitment elevates the quality of medical research for all of us. Best of luck with your analyses.